How are you all today?
Good, how are you? I just signed
Got what?
this, or
I got
my
no
performance
sleep.
from like 16:30, and then today
do we-
I looked and the nicest one is 16:36, which I
did the
want.
first
And then it was
There
like
any
signed
questions over the homework?
So I called him back. I was like, oh, that's again. Two.
12. We run through all of chapter 10 and 11. Do we have time for that?
Yeah, sure.
If not, you can just give me the answer.
Sure.
Class ends at 1 a.m., right?
Yeah. Y'all can stay till 1. I'll be out of here at.
I think the campus
8:45.
closes before that. I don't think we, I don't,
Yeah, they'll
physically, I
kick
don't
you
think we can do
They'll
that.
kick you out, man. So we finished 11.3 last time. We're gonna start with 11.4 today. It's our last section in our unit. So this section deals with applying Taylor series to do, calculus stuff. So and I think with the limit stuff that we see here, the first two examples, I don't think that's a shocking or a revelation in using a Taylor series to evaluate these things, because it's honestly easier to use L'Hopital's rule for limits of certain forms. But nonetheless, we'll take a look at this. And so it says evaluate the limit using Taylor series. As x approaches 2, x minus 2 over ln x minus 1. So just directly evaluating this limit, it ends up being 0 over 0. So that's a perfect situation to apply L'Hopital's rule to. However, we can find the Taylor series. For the natural log of x minus 1, centered at, where would we want to center that? At 2, yeah, because the limit is approaching 2. We want that Taylor polynomial to be accurate around 2, so we're going to center it at 2. They use a for the center, so we'll just say a equals 2. So this is where we go through that process. What's the function evaluated at 2? What's the first derivative evaluated at 2? Et cetera, et cetera. So just because we're a little bit behind, and there's some like this on your homework, but definitely won't be on your test. We're just going to write the series out for ln of x minus 1 centered at 2. And we're just going to pretend that we went through this whole process. So that's going to be, first term is x minus 2. Second term, we'll write out the first 3 or 4 terms. The second term is negative x minus 2 squared over 2 factorial. Third term, positive 2 times x minus 2 cubed over 3 factorial, minus 6 times x minus 2 to the 4th over 4 factorial. So remember, the only thing that actually comes from the derivative, the functions and its derivatives evaluated at a equals to 2 are these coefficients here. So we would get a 1, a negative 1, a positive 2, and a negative 6. Everything else is just in Taylor's theorem. Okay, so what we're going to do then is replace the ln of x minus 1 with this infinite series, and then compute that limit. Might need some more space, but all of that in for this. Just so we could get a better sense, instead of just looking at the first two or something. I mean, maybe with just the first two, you could see like what's going to happen, but just arbitrary, more than anything. Okay, so notice if we plug in the 2 through the limit, we're still going to get a 0 over 0, but we can simplify this quotient. If we factor out an x minus 2 from each one of these terms, then what we have is that factor on the top and bottom would cancel out. Does everybody see that? We're going to factor that out. Limit as x approaches 2. The top is just 1. The bottom, we've just reduced those x minus 2's by 1 less because we factored 1 out. So that first term would be 1. Then we would have minus x minus 2 to the first over 2 factorial plus 2 times x minus 2 squared over 3 factorial and so forth. And same story for all of those ones that we didn't list. Is everybody okay with that? Again, this isn't the most efficient way to evaluate this limit, but it is an alternative way to evaluate this limit. Now, as x goes to 2, this term, this term, this term, and all of those terms go to 0. So we just end up with 1 over 1, which is 1. For that limit. And I guess, this example is sort of showing us that if we do replace these functions with these infinite polynomials, the same results emerge from various computations. If we were to take that original limit and apply L'Hopital's, it's much more efficient, but we've got another way to think about these kinds of things now. Wait, x minus 1. So just to see that, we would say by L'Hopital's rule, we've got the limit as x approaches 2. I need to remember to save. The power was like going out, and so like the last class we lost all of our notes, so I have to remember to save. I'm not great at that, but derivative of the top, derivative of the bottom, simplify before we reevaluate. So it's pretty painless using L'Hopital's rule, but we can show that it is indeed the same thing as if we use Taylor series versus some other technique. Okay. I think primarily for us, where the Taylor series are a lot more evident as to why they're useful is when we start looking at antiderivatives, especially functions that don't have a known antiderivative. We can express those as polynomials instead. Did anyone have any questions on this example? Okay. So another limit problem, x approaches infinity on x sine of 1 over x using Taylor series. So we've got infinity, and sine evaluated at 1 over infinity is basically the sine of 0. So you have infinity times 0. We could use, again, L'Hopital's rule, rewrite that as a quotient. I guess maybe the most apparent issue with using a Taylor series here would be what? Yeah, where would we center it at, right? X is approaching infinity. So X is just getting larger and larger. You can't center something at infinity. So that's the problem. Initially, when we see like, okay, we'll use a Taylor series here, it's where should we center this at? Around 0? So we could think about this being centered at around 0 if we did something first. We couldn't just say center it at 0 because it's not going to be accurate as X approaches infinity. I mean, it would, but we would have to have super high order of terms. So I don't know that it's very intuitive at all, but we can make a substitution. You can substitute something in for what's already there.
B in for infinity.
Well, yeah, we wouldn't say like X is approaching B, because then we would have to say as X approaches B, what's the limit as B approaches infinity? You kind of have two limits there. I mean, you could do that in theory, but you're still poised with the same problem. Yeah.
Can you substitute 1 over x?
Yeah. Yeah, what would you substitute 1 over X for?
Just like a, and then, then you have x is equal to 1 over a. So then you'd have sine of a over a.
Yeah. Yeah. So like, see if this actually works though. If we're gonna say let a equal 1 over X, we would have X here being 1 over a, and then we would have the sine of a here, right? So if this is our substitution as X approaches infinity, what does a approach?
0.
0. So we have to also substitute in for that X in the sense of our limit. But yeah, that's the main idea, is if we perform this substitution, then we turn this infinite limit into a limit at 0, and then we can center the sine function at 0. So this limit is actually the limit as a approaches 0, 1 over a times the sine of a. And then we'll find the Taylor series. For the sine of something, sine of a, centered centered at 0. Since we're using a, we won't say our center is a. We'll just say centered at 0. So that'll definitely do that for us. We can now find the Taylor series for the sine of a centered at 0. So did anybody get a chance to memorize that yet? Is sine even or odd?
Sine is odd.
Sine is odd. So it's the odd powers of a over a factorial. Does it alternate or not?
Yes.
It's X.
Yeah. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So that's the sine of, we're using a though, so limit as a approaches 0. One over A times the sine of A as the Taylor polynomial. Now, you know, I don't think there's a huge disadvantage to not remembering these. I would strongly recommend you knowing those, the ones we started last class, because if you have to go through the process now, sine of 0, derivative of sine at 0, the second derivative of sine at 0, and you know, it takes a little bit of time just to generate a few terms. So much more efficient if you know these. Maybe we don't have to write so many terms, but oh, oops, that's unfortunate. Okay. And so then we see what happens here, distributing that 1 over A. We have 1 minus A squared over 3 factorial. A to the 4th over 5 factorial. So forth. But again, as A approaches 0, all of those terms after 1, all of those approach 0. So our limit is 1. You know, this you might remember certain limits from Calc 1 where you had to, you know, is like the sign of something that didn't exist. And in those limits, you would have to, like, more than likely use the squeeze theorem to bind that function in between two well-behaved functions. This could also be useful there, like if the sign of something that didn't exist, you could try this procedure as well, instead of trying to find bounds on the sine function. So L'Hopital's rule would also give us a limit of 1. But again, this is an alternative approach or alternative way to think about. Do y'all have any questions? Example 3 kind of builds upon what we talked about in the last section. We can differentiate and integrate the Taylor series. So we want to differentiate the series about 0, identify the function represented by the differentiated series, and then give the interval of convergence for that differentiated power series. So part A, I think it's beneficial to write out the Taylor series for the natural log of 1 plus x centered at 0. So once again, we could go through this process of finding all of it, or we could just here and find that as one of the ones on the table. 1 plus x or x plus 1. So we're looking at this series here. It's alternating, the powers match the number on bottom, no factorials. Valid for this interval here. So let's just go ahead and copy all of that down. That way we have all of the representations for this particular function. We'll just go up. We'll just do one more. And then we'll just write this as 4. All right, so for that, those x values, our natural log of 1 plus x is that series. And we want to take the derivative, we want to find the derivative of this. Since they're asking for, in part B it says identify the function and then represented by the differentiated series. I don't know that it's necessary to write all of these things out because really we're just going to be identifying this function, the derivative of this function. But if we have all representations of that, we can take the derivative of each part and we can see really quickly what all the terms are going to look like. And on the far right, we can see what the closed form or the series representation looks like. So we have the derivative of that is just 1 over x plus 1. Does that look sort of familiar? So the derivative of that function is that, but then we can also differentiate term by term. So derivative of x is 1, derivative of negative x squared over 2 is x, derivative of x cubed over 3 is x squared. Which is that. And then the closed form representation, we're taking the derivative with respect to x, so all we're going to do is utilize the power rule in that x to the k. Then we have we'll have k times x to the k minus 1 all over k. We see that those k's cancel out. So you just have this series representation. It's kind of weird. So what we're looking at here is what? What is that new series? It's geometric, yeah. The only difference is that it's an alternating geometric. Remember, the geometric looks like for x values that are in between -1 and 1. The geometric series is this series. So if we take this x right here and we replace it with a negative x, then we have that series there. But the series for the geometric is x to the k. We replace x with negative x, then you have negative x to the k, which is the series -1 to the k times x to the k, right? That's pretty much what we're dealing with here. Anyhow, I think it's worthwhile to notice those types of connections. So same series can be found if we just build off of the geometric and use composition, as if we start off with the natural log and take the derivative. You get the same series. All right, remember the natural log of 1 plus x was valid for, I'll just go ahead and write it here. That series was valid for the x values that are in between 1 and -1, including 1. But what's the thing when we take the derivative or the antiderivative of a series? What do we have to do? Yeah, you have to test the endpoints because you got a new series. These endpoints may work, they may not work. One may still work, one may still not work, but both of them could also work. So you've got to test the endpoints for the new series. So we're testing those endpoints in that our differentiated series. So really that's that's part B. We know what function is represented by the derivative of the natural log of 1 plus x, function representation, and its series representation. And then part C says give the interval of convergence for the new series that we have here. So for x equals to -1, then our series becomes this thing. And we just want to know, does this series converge or diverge? Converges, maybe diverges. So just, break this stuff up. You have -1 to the k times the other -1 to the k. This is also -1 to the first power. This one's also -1 to the -1. So -1 times -1 is +1. What about -1 to the k times -1 to the k? It's always what? Well, they're both to the k, right? Being multiplied, so can we write it like that?
It's always positive.
Yeah. And this is always just +1 right here. So that just gives us the sum from k equals 1 to infinity of 1. Does that converge or diverge? It what? It diverges, right? Because it's 1 plus 1 plus 1 infinitely many times. So this is a divergent series. Which means we exclude this from the interval of convergence. And our other endpoint was +1. In the same series. With that series, yeah. So we have 1 to the k minus 1, that's always 1. We just have the series that alternates 1, -1, 1, -1. Put these bounds here. So that series is really 0 if we add up an even number of terms, but it's 1 if we add up an odd number of terms. So since it doesn't approach a single value, it also diverges. Which means we're going to exclude this as well. So the original series included positive 1, the ln of 1 plus x. The differentiated series doesn't include positive 1. Therefore, that series equals, let's say equals 1 over 1 plus x for x strictly in between 1 and negative 1. That is, from the absolute value of x less than 1. So I think we should, just verify that with what we noticed earlier, that the geometric series converges for these values. And we simply said that this series 1 over 1 plus x is a composition of the geometric series. If we take negative x and put that in place of this x, what would that converge for? Same values, right? Because we're just replacing that x. We're just replacing this x with our negative x. So we just get, the reverse of that, but it's the same statement. It's still x between 1 and negative 1. So we could verify it, I guess, in that way. I don't know if that's a check or not, but we certainly have two different approaches, with the same result, I guess.
Accept that method on the test.
If it says differentiate and do all that stuff like the instructions said, yeah, that's what I would look. You have to differentiate, but if it didn't say, it doesn't matter. Any other questions on that? So I will say that from 11.4, this is the type of problem that will show up on the exam. I don't know if that's hyphenated. Exam-like question. Ish. Yeah, exam-like question. So let's, we'll talk about that in a minute. So evaluate the integral of e to the x squared from 0 to 1 using Taylor series or Maclaurin series. The issue, as we've mentioned a few times with the antiderivative of e to the x squared or e to the negative x squared, is that it doesn't have a known antiderivative. So then we really, at that point, you're stuck. Like, how do you evaluate some of these things that don't have antiderivatives? Because the fundamental theorem of calculus says in order to evaluate this, you have to find the antiderivative and then plug 1 in, subtract off when you plug 0 in. So we can find the Taylor series or the Maclaurin series, which is the Taylor series centered at 0 for e to the x squared. Where would we want to center this? 0? Why? Because it's a Maclaurin series. So does it matter? Like the interval from 0 to 1 isn't a huge interval. So if we centered it at 0 versus if we center it at 1, it shouldn't be that big of a difference in the grand scheme of things, right? When we can center things at 0, I think it's easier because you don't have that x minus 1 squared, x minus 1 cubed. You don't have that term hanging out. It's just x. Okay, so we'll use the Maclaurin series. Centering at 0. And so derivatives, coefficients, put that in Taylor series. Maybe you remember this one. But that's the first thing, is to find the actual Taylor series or Maclaurin series representation for that function, which involves derivatives, etc. What x values does that converge for? All x values, yeah. All x values cause this to be a convergent series. Okay, so if that's e to the x, we're trying to find the antiderivative of e to the x squared. So make sure you make that substitution. Let me do this. So then we have e to the x squared is going to be the same series. We're just replacing the x with an x squared. So it's 1 plus x squared plus x to the 4th over 2 factorial, x squared squared, x squared cubed, and then x squared to the 4th. And so forth. So you got to remember to make that substitution. Then what do? Yeah, we're going to find the antiderivative of e to the x squared by finding the antiderivative of each term of that polynomial instead. Let's write one more of these down. One more of these terms for e to the x squared. So that next term is x to the 10th over 5 factorial. So then keeping in mind that we are wanting the antiderivative, now we'll take the antiderivative of both sides. Oops. So the antiderivative of that is equal to the antiderivative of all of this.
Once again, do you have any number of terms you want us to do?
Yeah, so we'll talk about the error in a moment. Uh-oh. I literally copied the whole page.
Control-Z.
Yeah. All right, sorry, I was just trying to be a little more efficient with this, but I'll go ahead and I'll go ahead and write everything out. Okay. Okay, so again, we don't know the antiderivative of the left-hand side. We can certainly find the antiderivative term by term. Evaluating then from 0 to 1. Okay. So we have x plus x cubed over 3 plus x to the 5th over 5 times 2 factorial, x to the 7th over 6 times 3 factorial.
That would be 7 times.
Oh, yeah, sorry, thanks. X 7 times 3 factorial. X to the 9th, 9 times 4 factorial, and so forth. So then the question here is like, how many terms do we find the antiderivative of, or how many terms are we actually concerned with? And that really depends on the level of accuracy that you want. So let's just say that we want, and we should have stipulated that in the first place, but in general, this is what you're going to be looking at, and depending on what level of accuracy you want, if you want your accuracy to be like less than a third, we could probably stop here, because if we add these two, we're cubing that thing over 3, it's probably less than a third, but typically you want your error less than 10 to some negative power. So we'll just go ahead and stipulate that we want to evaluate this with an error of less than, we'll just say 10 to the negative 2. So then how that comes out in practice, we don't have to think about the error theorem of Taylor's or anything like that. We just have to say, well, if this is the integral in question, and I know that's my antiderivative, then let's just plug in 0 and 1, because we see half of it's gone, right? Half of it's just 0. So we're going to plug in 1 for our x. Just going through with the fundamental theorem. We have 2 factorial is 2, so 1 over 10. 3 factorial is 6. 42. 1 over, what's 9 times 4 factorial?
216.
216? And 11 times 5 factorial?
1320.
1312. 1320.
1320.
Oh, all right.
You're right. This one is right, but I did it wrong.
Okay, so then we've just applied the bounds to our infinite polynomial. And then since we want the error to be less than 10 to the negative 2, all we've got to do is look for which term would cause us to add past that, or which term affects the 10 to the negative 3 place.
Where'd the 1 come from?
Oh, you have an X.
Yeah, where'd the x come from?
What x?
So,
Antiderivative of 1 is x.
Yeah.
Oh, yeah.
Never mind.
Yeah, that's the biggest mistake. People find the power series for a certain function, and then they just totally forget to find the antiderivative of each term. Like, that's by far the biggest mistake on this type of problem I see on the exam. So yeah, I mean, it's common enough for people to easily overlook. So we want an error less than 10 to the negative 2, and all we do is go look for this term here. This term here is going to give us an error of less than 10 to the negative 2, because that's going to affect these subsequent terms are going to affect the third decimal place, the fourth, the fifth, etc. So this term right here, since this term is less than 10 to the negative 2, for that particular level of accuracy, we'll just say that the antiderivative from 1 to 0, or the integral from 0 to 1 of e to the x squared dx is approximately 1 plus a third plus a tenth plus a 42nd plus 1 over 216. Because if we stopped at 1 over 42, is that gonna be something less than 10 to the negative 2? No, clearly not. 1 over 42 is clearly greater than 1 over 100. So we wouldn't want to just stop with 1 over 42. We want the first term that's less than that specified error in the mix. And then so what we get here for this, the fractional pieces here, 1.461 772. All right, and that's pretty much all we're after. Write down the exact value just so we have something to compare to. But that's pretty much the idea. Does anyone have any questions on what we've done, why we've done it? And just put this in a Wolfram Alpha, I think it was. The actual value was 1.462. 65. So we see we're off in the 10 to the negative 3 spot. So there's a lot more that series do, but it's kind of like, you know, that's it. That's the apex of why we did all this stuff. Just for a list, I think we can find a list here. Functions. So Wikipedia is calling it a non-elementary integral. So here's a couple of functions. I mean, that's just a few functions we couldn't find an antiderivative for. So we can express these functions as power series as well. Okay, let's see, yeah, the last two questions, they give us a series and it says, identify what function is represented by the series. So with these, most of the time, you just want to like break them up, and the more familiar you are with certain types of series, the better off these questions are going to go. So just to kind of see how this works, we would want to take 2 to the k and x to the 2k plus 1 power. We'll put this in front of this series in a minute, but we just want to kind of break this up as much as we can, just to see we have x to the 2k power times x. And then thinking about this x to the 2k as x squared to the power of k times that other x. There, yeah. And then we've got 2 and an x squared to the power of k. So we're just going to write that as 2 times x squared to the k times x. And then that series that we started with is this series. And notice that x that we're multiplying by didn't have a k associated with it. So we might as well just put that out front. What about this piece here, this 2 times x squared to the power of k? Do what? Yeah, you could look at it as a u substitution. If that were u to the k, what kind of series are we looking at here?
It's geometric.
It's geometric, right? Geometric is just something to the kth power, where each term is a product of or is a multiple of the common ratio. Here, the common ratio is 2 times x squared. So with the exception of that x hanging out front, that's just going to have to be our multiplier. We're multiplying by power of x. But the series itself, being geometric, can we just think of it as r to the k? What would that series be? Like, what do we know r to the k is for specific x values? 1 over 1 minus r, right? So this series is 1 over 1 minus the ratio 2x squared. I'll get that equals. So there's our function. We've identified that function that's specified by that series. It's x over 1 minus 2x squared. That's the function. So it's just kind of like working backwards from a few examples that we did in the last section.
So if you didn't really split it up at the beginning, like you did, what other would be your first step? Because I'll be honest, I wouldn't have seen it quite like that.
Yeah.
Let's just get back to algebra.
That's pretty much it, man. Yeah. Yeah. So some of these types of problems are like super difficult.
Are we gonna see something like
You
this?
got things like this.
Probably not. Nothing like super difficult. But if that's kind of the idea, not all of them are geometric, but that's kind of the idea, is to sort of fit them into something you already know. Like, oh, hey, that's alternating, or that looks like this thing to the second power over 2 factorial plus that thing to the third power over 3 factorial. You know, so that's when the knowledge of those particular series is really helpful. So you're recognizing some fundamental pattern and then saying, oh, that's just this series with that substituted in, or, you know, whatever the case is. So we're going to do the same thing here with this expression. And and maybe this one's a little more straightforward, because we have all of this stuff to the kth power, right? It's x squared over 4 times the negative 1. All of that's to the k. So we're going to write the negative 1 times the x squared divided by 4, all to the kth power. And so we're dealing with that series from 0 to infinity. And again, that's just a geometric series with negative x squared over 4 being the common ratio. So we would say that this is 1 over 1 minus the ratio. And that's our function. Or, if we were to rewrite this function, it's 4 over 4 plus x squared. So typically, we're not working this way with functions and series. We're usually starting off with a function and saying what series is represented by that particular function. So it's not something that's super common, but there are like 1 or 2 homework questions about this. Yeah.
On a test, if we left it as 1 over 1 plus x squared over 4, would we be marked down?
I think that would be fine. Yeah.
We already said this is not going to be on the test. Right?
Yeah.
Oh, so never mind.
Yeah. I don't know. I've graded like 2 of your exams so far. Like I guess y'all think you must think I'm a picky grader or something because y'all ask me questions like that. But I don't mind stuff like that. Like I'm not super strict about how something's represented
So it just
in
depends on the
general.
student.
Huh?
It just depends on the student that did it.
I don't know the student because I literally grade 1 page at a time. So after I turn that first page, unless you have like super distinctive handwriting, I have no idea whose exam I'm grading.
Write my name on every page.
But that's pretty much it. We primarily want to focus on the antiderivative stuff, the definite integral stuff with the series, the Taylor series. Does anyone have any questions? It's by far, I think, a whole lot easier to actually use these things in practice than it is to develop all of that theory to actually be able to utilize them. So how about we'll take a break? I actually already wrote out the content of the exam just to post on D2L later, and that way we'll maybe have more time because there was a little bit of stuff I had to write out. There's 2 pages of content for the exam, and then that way.
Sequences.
Ooh. Handwritten order.
You should be like this girl instead of Brady.
What do you think?
Brady Lynn Gabriel,
don't
born
pass
4/22.
Just curious, what do you think?
Oh, we're not allowed anything from chapter 12?
Attendance.
Yeah.
So at the end of the semester, if someone has an F or an F, someone has an F, then I have to put the date of last attendance for that person. So that's the only reason I take it.
You should give a bonus.
Is that
Because if somebody's like, oh hey, I failed the class and it was unfair to me, and then I say, well, you didn't show. Last time you showed up was in September, so it's just CYA kind of thing. All right, so the first couple of 10 problems on the exam will have to do with that of a sequence. And remember, it's quite a different thing when you deal with a sequence versus a series when you're adding those terms up. So the limits of a sequence are just computed. These are all limits at infinity, k or n or whatever. And whatever you get as a result on that sequence is the limit of that sequence, because the sequence is just a list of numbers. You're not doing anything to those numbers but listing them out. So the limit at infinity, state if a given sequence converges or diverges. 4 of those problems, same thing. You just compute the limit at infinity. Whatever you get, if it's not infinity, then the sequence converges to that number. You should be familiar with the concepts of converging monotonically via oscillations or whether it diverges. So monotonic was a sequence or a series that does what? Yeah, like this or like this, right? It means remember, monotonically means that it's either non-increasing or non-decreasing. In other words, it's either decreasing and constant or it's increasing and or constant.
But for converges, that means it's not increasing.
Say that again.
For converges, it means it's specifically not increasing.
That's for series. So like for certain series, we had like statements that said things to the effect of like a non-increasing series is bound between successive partial sums, stuff like that. But that's not explicitly true for a sequence. You know, if we have a sequence that's given to us, and I don't know, like visually, it's just something like this. Like it's increasing and then it's flat and then it increases again. That would be a monotonic sequence. So they're just, if we graph a sequence, it's just a list of ordered, it's just a bunch of discrete points. They're not connected. We're not adding them in any way or anything like that. And then the rest of the stuff is about series. So the intent really is that these 10 problems here should go by pretty quickly. It shouldn't take too much time to compute. And then the rest of the stuff is about series. So we should be able to state if a given series converges or diverges. That's going to be 2 problems. Those should be like highly recognizable series. So you shouldn't really have to question whether they converge or what test to use for convergence or divergence. You should know there's convergence or divergence of both the harmonic and the alternating harmonic series. You should just know those. The harmonic sometimes comes up in comparison tests, but you should know those 2 series for sure. There's actually another sequence question here. You should be able to find the recursive formula and the explicit formula for a particular sequence. That was, we dealt with sequences in 10.1 and 10.2. There's a little, 10.1, remember, was like a, sort of like a preamble to all of it. So it had a little bit of sequence stuff and a little bit of series stuff. The bulk of the sequence stuff showed up in 10.2. But the recursive explicit formula stuff was in 10.1. There's 2 problems finding the sum of a geometric series.
Can you go back for a second?
Yeah, I'll post all of this after class too. The sum of a geometric series. So this is, again, something you should definitely know. When we started looking at like Taylor series and stuff like that, we sort of looked at just x to the k or r to the k, and we just had 1 over 1 minus r. Remember that a is like a constant that's multiplying the entire series for r to the k. So it's 1 over 1 minus r, all of that times a. If the absolute value of r is less than 1. And a is that first term. Because the way the geometric was defined in this textbook was starting at k equals to 0. So that implies that your first term would be a, whatever that constant is. So if you're gonna, here's an example here. If you're gonna find the sum of the geometric series 5 over 4 to the k, then there's a couple of ways to look at it. Either you can shift this index so that it's at 0, and then we can apply this formula as it is, Or we can just say, what's the first term of that series? 5 over 4 cubed is the first term, because this starts at 3, and the common ratio is 1/4. So then we would plug in a over 1 minus r to find the sum of that particular series. We did a couple of examples like that as well.
What section were those examples?
That was series geometric was 10.3, I believe. 10.3. There's going to be one problem where you have to use the integral test to test for convergence or divergence. And with the integral test, you should know what conditions were in the assumption that the given series or the given function has to be positive, continuous, and decreasing. And you should be able to justify those 3 conditions. It's not going to be sufficient enough for you to just integrate the thing and say, oh, the integral converges, then the series converges. I really want to see justification of those 3 conditions. The decreasing, depending on the problem, and we saw a couple of series like that, I think, like k over ln k. When we compare that to like k plus 1 over the ln of k plus 1, I don't know, to me it's really not obvious which one's larger or which one's smaller. It's not, those kinds of things aren't as straightforward as saying 1 over k squared compared to 1 over k plus 1 squared, where this is clearly smaller than this. In situations like this, if that's your series corresponding to this function, then you need to justify that it's decreasing. You have to be pretty thorough, or just use the derivative, the first derivative test. Positive, usually that's pretty easy to verify that the terms of the sequence, or the series rather, are positive. Also, continuity is pretty straightforward too. Discontinuities only show up if we're taking like negative even roots of negative numbers dividing by 0, taking the log of 0 or negative numbers, the typical function stuff. So those 2 are pretty easy to justify. There's one series that's telescoping. So with telescoping series, you find the nth partial sum, the formula rather, for the nth partial sum, and then use the limit at infinity on that formula for nth partial sum to state whether the given series converges or diverges. And the idea is something that you should be familiar with, not just for like the telescoping series, but if we have the sum of a series, and we can express that as, we can express the nth partial sum, then the limit at infinity on the nth partial sum is the actual sum of that series. It's just, we didn't do a whole lot with the nth partial sum stuff because most of the series that we dealt with, you couldn't really find an explicit formula for that. With telescoping series and with geometric series, you can certainly do that. And those were really the only 2. So one of those questions for a telescoping series. Remember, we saw a couple of variations of the telescoping series, but basically you have to have something minus something else for any cancellation to occur. Those could be presented, as this thing minus this thing. It could be a logarithm of a quotient that you can turn into subtraction. It could be something where you have to find the partial fraction decomposition. So I would be familiar with those. So one problem where we have to use the alternating series test to determine if a series converges or diverges. State and justify the 2 conditions that are here. These were the conditions for the alternating series test. Remember, the thing about the alternating series was that the alternating series was presented as, you know, this alternating part with our a sub k attached to it. So when we test whether an alternating series converges, excuse me, by the alternating series test, you don't take in consideration that -1 to the power. It's just the everything but that is what you're testing in these two conditions here. Does anyone have any questions at this point? This is definitely a lot of material on this test. Not to like discourage you or to scare you or anything, but usually it's the worst test out of all of the tests we take, even the final.
I did have a question about the final. How much percentage of this test would be on the final? Like, because the final replaces the lowest grade.
Right.
So if this test is just a wash and it's the lowest grade, how much of that are we going to see
Yeah.
on the next test?
I'm not sure yet. I haven't thought that far ahead. I don't know.
So basically, if everyone fails this test, then most of the final is going to be this test.
No.
Okay.
Definitely not. Definitely not. We have chapter 12 to put on the final too, so we have chapter 6, chapter 7, chapter 8, 9, 10, 11, and 12 on the final. It's going to have to be pretty sparse for certain things.
So you go up just a little bit.
Yeah. Yeah. So like these, this item 10, no test will be specified. So you know, like the root test, the ratio test, you should be aware of what situations those apply to. Hopefully, after you've done all of the homework, you've got a good sense of what you're doing. So no test will be specified for those two problems. Let's see, yeah, that's all. Good. Use the comparison or the limit comparison test to test for convergence or divergence. I would be familiar with both, but also know that the limit comparison test is a little bit more user-friendly because you don't have to establish some sort of comparison between the kth term and the kth plus 1 term. The limit comparison, it doesn't really matter. Like I could compare a geometric series to the alternating harmonic series if I wanted to with the limit comparison.
And on that one, we can pick which one we want.
Yeah. Yeah. And so like on certain problems like this, using a comparison test, I see people use a comparison test. Personally, I think it's easier to use the limit comparison test, but if you're going to use the comparison test, just make sure you're well aware of its conditions, because its conditions are different than that of the limit comparison test. One question where we are given a series that has a variable in it, like x, we want to be able to state the radius and interval of convergence. And primarily that's when we use the root and the ratio test, the absolute value of that, from 11.2. One of those problems. Find a fourth order Taylor polynomial centered at some value a for whatever function's given to you, and then use that approximation to find, or use piece of 4 rather to approximate the function at a particular value of x. And so that was 11.1. There's going to be 2 problems where you have to find the Maclaurin series for a given function. and keep your answers in sigma notation. So those, you should know the series that I've listed here. The series for these can really save you a whole lot of time.
How many problems?
2. If you don't remember those Maclaurin series on the table for those particular functions, then you have to go through the process of finding the derivatives and evaluating at A, which takes a bit of time.
Can you run through sigma notation? Sigma notation?
Yeah, so like if we know this one here. Like if you know the 1 over 1 minus x is this 1 plus x squared, equivalently know that it's this summation. Or if you're not going to remember that, if you can write out the polynomial by finding the derivatives and evaluating, you should be able to write out the closed form or the sigma notation of that particular series. And then one problem using a Taylor series to evaluate a definite integral to a specified error within a specified error. So I think one thing you definitely should also know is when we started talking about limits of series or limits of sequences as well. The limit at infinity for the one that was 1 plus I think we had a over n to the power of bn. I would know that one for sure. Otherwise, that's, we've done that in class a few times. If you don't remember that, then it's a pretty lengthy L'Hopital's rule problem to justify. But what was this limit? Yeah, so I would know that. Yeah, that's the more generic of the two. Yeah, and
When is that going to come up in the test?
do what?
Wouldn't that be useful?
It might not be useful on the test, but it might be.
Oh. I'm definitely gonna
Some maybe
have it
number.
and then just not.
Yeah, like
recognize it.
For sequences, like if that's a sequence, if it says find the limit of that sequence, like that's.
So it's important.
If that's a sequence and you're using the divergence test to test whether it converges or diverges, if that were a series, and we use the divergence test on that and saw that, well, hey, the limit of that term is not 0, therefore by the divergence test it diverges, you're done with testing that series for divergence or convergence. Let's see. Yeah, I think that's kind of the highlights. Are there any specific things that you'll want to talk about or look at?
You said the test was written out?
Huh?
The test was written out?
Written out?
Yeah.
What do you mean?
Like you've already written out our test?
Yeah.
Can I see?
Well, if you just want to leave it and leave the room.
Yeah,
and-
sure. Sure. Are you
super helpful.
gonna pay for me to retire if I do that?
How close are you to retirement?
23 years, man. They give me it's pretty sweet working for the state. So you gotta You gotta come correct.
Oh, I know.
Yeah.
Aside from that, no.
Yeah.
There's another limit I ran into where the limit was 1 over E. And I think it was something like 1 plus 1, or 1 plus 1 over x plus 1, or x minus 1.
Like that?
I think so.
And it
that
was
to the power of, I think x.
X, okay,
I
and
may be
then,
remembering this wrong, but I was trying to figure out where the next step was to take, and then I found out that the next step was just, you should know that limit. And it was just 1 over E.
yeah, I think 1 over
Yeah.
E, I think I had different representation. And like so this would be like a L'Hopital's rule problem. If you're not sure about that,
I'm not sure about that.
you know, the n over n plus 1
Yeah, it was just that.
to the n. Is that maybe it?
I guess just like, I just got stuck there, so.
Is there like a list of limits that would be good to memorize?
Other than this one we wrote up above, I think it's hard to say because they all take varying forms. There's really only 2 forms at the end of the day that L'Hopital's applies to, and so the other limits that come out to be so limits like 0 times infinity. Those limits, I mean, I think L'Hopital's is absolutely worth knowing. But these limits arise when you're taking like I'll just use n for, like if we have the product of 2 functions of n, that's where those limits arise. But in order to rewrite this so that it applies to L'Hopital's, then that's when we have to reciprocate the other one and then divide by it. So if this product is 0 times infinity, then this quotient will always be 0 over 0 or infinity over infinity, depending on which one you chose to leave alone and which ones you chose to reciprocate. So that's how we take those back to a form of 0 over 0 or infinity over infinity. The ones that are kind of like this, where it's like n to the n or x to the x, those are kind of like once removed from this process, because those are the ones that look like 1 to the infinity, 0 to the 0, or infinity to the 0. Again, coming from limits that look like f of n to the power of g of n. And these are the ones that we rewrite like this. That's in parentheses. And we simply rewrite that because it's really not exponential and it's not a power, but rewriting it in terms of inverses e and ln now turns that thing that's f to the power of g, and now turns it into a multiplication problem. So when you rewrite this, then you're directly back into this situation here. Well, it's actually this situation here. And then you have to rewrite it using the quotient, the reciprocal of the quotient, rather, of one of those.
Okay, and so if you have that situation where it's e, and then to the power of, but you take the limit, it's infinity over infinity, then you just apply L'Hopital's rule just to that power.
Yeah, right, exactly.
Okay.
Yeah, so then you know, if you want to see this like a generic step further, then it's okay. Then it's really e to the power of ln. We usually leave alone. divided by 1 over g. So I mean, that's really the ultimate goal of rewriting those types of limits. It's as e to that power. You're just computing the limit on that power. And for sure, if it is of that form and you rewrite it that way, for sure it will be 0 over 0 or infinity over infinity here at this point. But yeah, so like this thing here, it's 1 to the infinity if we try to evaluate it. But I think if you looked at it like, this is the same thing as the limit at infinity of, we'll rewrite our expression here, n over n plus 1. We'll rewrite that as n plus 1 over n to the power of negative 1. And then so what we're actually looking at there is the limit at infinity for, so some of these you can be, you know, kind of tricky with, you know, or clever with, and say that's really n plus 1 over n to the negative n. And we see that n plus 1 over n is really 1 over 1 plus n. Or sorry, 1 plus 1 over n rather, when we simplify that. So that's 1 plus 1 over n to the power of our negative n. And what would that limit be?
That would be 1 over e.
1 over e, right? A is 1, b is negative 1. So that's e to the 1 times negative 1 power.
That's crazy.
So you don't have to be clever with it, but I think it's, you know, it's sufficient sometimes to be that way. Otherwise, then yeah, you're dealing with this hideous situation where you've got to go, you know, it's twice removed from L'Hopital's rule. Yeah. So yeah, probably worth knowing that.
Really, yeah.
So that's maybe what you were talking about. Somewhat close. So where do we put that? I don't know where that went. Oh, there it is. Yeah, any other things you want to talk about?
You should give us practice problems that are very similar.
You know, very similar. Yeah, I think if you're able to, if you have the time to go through the D2L assignments, not the assignments, but the exam 3 review could be helpful. But again, there's a lot of questions there.
Do you get your problems from D2L or do you make them? Or like from my math
I
lab?
get them from our textbook, and then the problems that I incorporate in your homework and in the exam study reviews come from the textbook.
Interesting.
I don't know. I think if you like compared some of your homework questions to the actual exam questions or quiz questions, you would probably see that the exam questions are kind of easier than some of the homework problems and the quiz problems for sure.
It's definitely easier than the quiz.
Yeah. I don't know what I'm doing. Yeah, so there's, you know, you don't have to do all of these problems. I wouldn't say that these are reflective of the exam. There's blocks if you're cool with like, oh, I'm good with ratio tests and factorials, then you just skip those 20 problems, right? But I'm not saying that if you do this,
I usually do like
that problems from the exam will be on here.
like every like.
But it's certainly the more of these you do, the better off you're going to be. Like I really didn't study well as in college at all. Like I would literally do all of the problems in the textbook the night before the exam. And that's really good for short-term memory. That's good for short-term learning, which is fine. If you don't have to remember this stuff ever again, your cramming probably works for you. But if you have to remember this stuff at some other point, and all you ever done is crammed, your long-term memory is going to be shot because it just doesn't lend itself to long-term memory. So, anyways, most of you probably won't be math teachers, so you don't have to worry about it. But I kind of did, and I was like, oops, should have studied differently. But yeah.
You seem to be doing okay. I think with doing it every day helps.
Yeah, right. Yeah, exactly. Totally does. Any other things y'all wanted to look at, talk about?
Can you do one where you adjust the index?
So adjusting the index, I'll take this one here, this geometric one that we had on the first page. So the idea of shifting the index is sort of this opposite relationship to the thing that you're summing. So whatever's in front of the summation, if we want to shift the index and say, all right, well, I don't like my geometric series starting at 3. I want my geometric series to start at 0. MyMathLab is going to tell you, make a substitution, let W equal K minus 3. But it's not even really that complicated. If I want this to start at 0, I've had to subtract 3 from my index. So what I have to do up here is add 3.
Wherever you see K.
Wherever you see K, that's it.
Why would you want to like necessarily do that?
So this one here, then we would say that the first term is 5, right? That's our A. The first term is 5, and then our ratio is, well, what would our ratio be here if we wrote it like that?
Same.
So here A is equal to 5. Yeah, so this is, we'll put that 5 out front if we need to. I don't know that we need to, but we'll go ahead and do that. But this is actually 4 to the power of K plus 3. Right? When we look at the geometric, it's presented as something only to the kth power, right? So you've got to think of this as 4 times K, right, times 4 to the third. So yeah, we totally misspoke, but I think it's good that we did, because the first term here isn't actually 5, because the 4 to the third is also a constant. So the first term is 5 over 4 cubed, just like we have here. Common ratio is just this 4 to the k. It's 1 over 4 to the k. But so like shifting indices, I don't know that it is beneficial sometimes, but I don't think you would ever have to do it. I mean, some of the ones where in MyMathLab, let me correct this. Some of the ones in MyMathLab where they say, shift the index, like the one we talked about in class the other day. How many terms of the alternating series do we have to add? The things that we did in class is enough to say this is how many terms we should add. But if you're looking at help me solve this, it's going to say shift the index so it starts at 1, and it's totally not necessary. Because this geometric series, whether it's at 3 or at 0, this statement is always true. It's just when it's presented as a over 1 minus r, particularly corresponding to k equals to 0, then it's misleading if it starts at 3 to say, oh, well, I know what my a is and I know what my r is, because it's not the same, especially that initial term. The first term a will not be the same if I start this at 3 versus if I started at 0 and don't shift the index, right? Like if I start this 5 over 4 to the k at 3, then I have an initial term of 5 over 4 cubed. But if I start this at 2, then I have 5 over 4 squared as the initial term. So that's really the only thing that changes. Shifting the index in this situation is just for aesthetics, I think, right? Because it's like, hey, I'm used to seeing my geometric series starting at 0. Is that helpful?
Yeah, I wrote down what you wrote and I was like, maybe don't do this.
Yeah. Yeah. I think particularly with geometric series, just plug in that value of k to see what your first term is. That's the a. And then there you go.
Cool.
Yeah. Any other questions or comments, problems you want to look at?
Can we go over sequence notations?
Sequence notation, what do you mean? What, like, particularly, what are you thinking about?
Like, on 10, 1 is big sequence problem.
Okay.
Infinite series is partial sums. First we should decide.
Okay, you mind if I take a look?
Well, I think you're not done.
Okay, good. I can decipher it.
You said to consider that.
Oh, okay, yeah, and then.
The only two pictures.
What?
You said that the is cute.
Oh, yeah, so the necessary and sufficient conditions, sorry.
And that's the sum.
So that you don't really have to worry about the necessary and sufficient conditions. I was just using that because a lot of times when people, and even on the exam, when you're given a series, and it says, determine whether the given series converges or diverges, a lot of people will just apply the divergence test and make the wrong conclusion. And they'll say, all right, well, the divergence test on this series, since that's equal to 0, that means it has to converge, and that's absolutely not true. So that's why we talked about necessary versus sufficient. So the terms of this series, the series eventually approach 0, but that doesn't mean that the thing converges. So for a series to converge, it is necessary that the terms approach 0, but it is not sufficient enough to guarantee convergence. That was the main reason I chose to talk about the differences between necessary and sufficient. But as far as like testing on that, I won't test you on that.
Did you ever find out what term hits 0 on that?
What?
Like what numbered term hits 0?
Never.
No, because it actually never is 0, right?
Yeah.
It's only out at infinity that it's 0. So remember the limit, that's, like a fundamental thing about a limit, it says as k gets larger, 1 over k gets smaller. That's really all that's saying. As k approaches infinity, 1 over k approaches 0. It's never actually 0. So this right here does not imply convergence. So make sure you're not misinterpreting the divergence test. It's a powerful test when it works, but more often than not, it's misinterpreted than utilized correctly. The only time the divergence test works is if the limit at infinity is not 0. Then we can say it diverges. That's the appropriate application of, for a given series. Anything else? Yeah.
So for the first 3 things you said are going to be on the test, it just kind of says state if it converges or diverges. Can you literally just write or converges or diverges?
Yeah.
Do you have to show work?
No.
Okay, cool.
Yeah, the first 2 things for the series, the sequences rather, All you have to do is say that it converges or diverges. You don't have to, unless you want to, or if you're unsure, show some work, but I don't require work on those.
Would you say the integral problem is usually the one that's gonna like take the most amount of time, or that like people lose the points on like more often because of the conditions?
Yeah, not necessarily. It's really like a grab bag as far as what's, you know, what's commonly missed. It's kind of all over the place. It's not usually like the, you know, like the other tests where it's like, yeah, integration by parts or whatever is usually missed. It's kind of random.
What are the things you would look for?
Hmm?
What are the things you would look for? Like if you were getting prepared for it or something? Like what would be the things that you would consider as like, this is something worth missing?
Worth missing?
Why am I missing?
Oh, that people might miss?
Yeah.
Yeah, it's really anything.
Well, I mean, like in your case, like if you were doing the problems, what would you encourage them miss?
I don't honestly know. I think the sequence stuff is pretty easy.
Choose.
Yeah, I can't answer that. Kevin? For like telescoping series, all right.
Well, yeah, the reverse, like whatever.
And I don't have one off the topic.
For the
Off my
problem,
head.
you were like, when you're going over it, you're like, know how to do partial fraction decomposition and properties of logs. What else did you say?
Like a series that just has like the sum of 1 over k minus 1 over k plus 1. Those should be immediately recognizable as a potential telescoping series.
Okay.
But the log ones and the partial sum ones are like telescoping. Sometimes they're telescoping series in disguise.
Cool.
And like writing the like reverse, the summation.
Oh, this doesn't work. Let me do that one. And so, like, what I would do for this one, or any of these that actually... okay. Try that again. Okay, so telescoping series, find the formula for the nth partial term of the sequence of partial sums, evaluate the limit at infinity on that. So what I would do with, let me write down the indices, 1 to infinity. What I would do on this one is just factor that 12 out. I mean, if you want to leave it in, there's nothing wrong with leaving it in. Maybe leave it in, because if you factor it out, you'll probably forget to multiply it in later. But I would factor the 12 out. Just, you know, this is something that you would probably see if you had to do a partial fraction decomposition, in the hopes of a telescoping series emerging out of something that you're using partial fractions on. You know, A has to be some number, and B has to be the negative of that number. We wouldn't get something like this from a logarithm. But the idea is you write out the first few terms and the first and the last few terms. So when k equals 1, and I mean we could simplify these, but I'm just going to leave them. K equals 1, k equals 2. And it's up to you how many terms you want to write out. K equals 3.
I would guess like at least 3. Because then it's like on the end part, it's not even the beginning part, it's like I don't even it's so much like.
Really, you just need to write out as many terms until you start seeing the pattern of cancellation. And so we would have this term canceling with this term. And that's kind of all you need. Each term consists of a pair of numbers, right? And so I don't know how you label these, but what I say usually is, all right, well, if I'm talking about each pair, I say that the second one here cancels with the first one, that's 1 to the right. So 1 to the right. And then consequently, that gives me that the first term cancels with the second, that's 1 to the left. So I get kind of a 2 for 1 here. But since you're after the nth partial sum, you should take your sum all the way, well, you can't, but you should stop at the nth term when k is equal to n. So that's, to find the nth partial sum, we have to stop at the term where k is equal to n. And so we see the cancellations are the ones that are like right next to each other. So go back one term when k is n minus 1. And write that term out too. So we have 12 over n minus 12 over n plus 1. And then 12 over n minus 1 minus 12 over n. And then you just cancel stuff. Those are gone. Those are gone. Will this cancel with something? Yeah, so that's the second in the pair. The second will cancel with the first, that's 1 to the right. So this will cancel with this term right here that we didn't write down. And so on and so forth, that would continue. We get to this last one. Does the 12 over n plus 1 cancel?
No.
No, so we'll keep that. Does 12 over n cancels with this one? Does the 12 over n minus 1 cancel?
Yes.
Yeah, so that one cancels. It's the first in the pair. It's going to cancel with the second term that's 1 to the left. So this thing canceling with this thing. The other thing that didn't cancel was our very first term. Was this 12? Oops. Was this 12? So what's the nth partial sum for this telescoping series?
12 over 1 minus 12 over n plus 1.
Yep. So it's just 12 over 1 minus 12 over n plus 1. That is S sub n. And then so the limit as n approaches infinity on the nth partial sum is the sum of any given series. So that's the sum of our series at this limit at infinity. So that limit should just be 12, which means the sum is 12. Is that kind of...
And well, besides the telescoping series, there's only a few that we can actually do that on.
Yeah, the telescoping and the geometric. But we already have the formula for the geometric, so...
Right.
Yeah. So that's kind of initially how we developed the formula for the geometric, but then we started looking at the a plus r squared, and then we said that's S sub n, right, and then we multiplied. So we were able to like prove that formula more effectively. But yeah, telescoping and geometric for the nth partial sum.
What if you like shifted the n plus 1 value to the very end? Like if it was n plus 1 minus over m plus 2 at the end?
So like if we had an additional thing out here,
Yeah.
or just this thing right here in pink.
Like, well, if you had like another one to the right, basically that one would cancel out, but you'd just be left with at the end negative 12 over n plus 3.
Yeah, so if you're talking about if we looked at the n plus 1 term, instead
Yeah.
of stopping at the nth term. Yeah, so what would happen there if we did that? Then the 12 over n plus 1 would cancel out, and we would have 12 over, 12 minus 12 over n plus 1. And then that's, if we said that's our nth partial sum, it's technically incorrect, but you say that the limit wouldn't be affected,
Yeah.
right?
So basically, the ends on the bottom just have to like be in the same form as the original.
Right.
equation.
That one would be like the n plus 1 partial sum.
Yeah. So that if we stop there, that would give us a formula for the nth plus 1 partial sum, which there's nothing wrong with that. It's just you're doing a little bit more than you have to. Because if the limit on the nth partial sum approaches 12, then the nth plus 1, the nth plus 2, the nth plus a millionth partial sum would also be 12. So yeah, if you went too far, it's not going to be detrimental if this series is convergent. And if it diverges, it wouldn't be detrimental either. But you're kind of just adding additional information that doesn't necessarily need to be there. But there's nothing wrong with it. Is that where you were? Did that answer your question?
Yeah. Well, so if you had like a question like this, your question would be like, what would it diverge to?
Yeah. Well, it would just be, hey, here's a series. State whether it converges or diverges. Yeah.
So it would, I don't know, I was just wondering, like, if we had to write out that specific equation, like, would we need to have, like, it goes to 12 minus 12 over m plus 1?
Yeah. If you were going to stop there.
Nth partial sum.
Yeah. And yeah, again, the reason we stopped at n was because this says specifically evaluate the limit at infinity on the nth partial sum. It may say that on the exam, it may not. But again, the overall idea with any series, and I forget where we wrote it out, but the overall idea with any series is that if you know the formula for the nth partial sum, then you know the sum of that series. So that's really the main idea. And again, this thing's actually, we could stop this at n if it's an infinite series, because this is the same thing as saying this right here. So like if we're able to find that nth partial sum formula for this series, then we can compute the limit at the limit at infinity, because this actually represents the sums. If we just look at the limit on the terms, then we're in a divergence test situation. So that's the reason it works, because with this partial sum, we are literally looking at the sums. With the a sub k, we're just looking at each term of the series, not the sum, which is what a series is. Yeah, so I think that's an important distinction to make between, why does this actually give us the limit or the sum of the series when I compute the limit on a sub k and it doesn't give me the limit of the series? That's why, because you're just looking at the limit of each term as opposed to what the sum of each term is. I hope that's clear. Any other questions? Oh, good to go. Would y'all mind doing some student evaluations?
We'd love to.
Because they're due pretty soon, and I'd rather not give them at the end of the right against the